Hi everyone! Today we're starting Module 4, and this module is all about types of reactions. So previously we did discuss some types of reactions, so the five main types, but today we're going to dive a little bit deeper into different types of reactions. So in this module we're covering sections 9.3, 11.1, 11.7, and 7.3. So previously we talked a little bit about solubility, and you might remember that solutions contain a solute and a solvent. And the solute is the minority component of a solution, whereas the solvent is the majority component of a solution, and typically the solvent is water. So if you have a cup filled with water, let's say we add some sugar to that water. The sugar is the solute because it will be dissolved in water and it's present in a smaller amount, whereas water is the solvent. So we can make a lot of different solutions, and again, whatever is present in the smallest amount is the solute. Whatever is present in the largest amount is the solvent. So you could mix two liquids together or two gases together, and whatever's present in the smaller amount is the solute. Now, solubility is the maximum amount of solute that dissolves in a specific amount of solvent. So typically we express that in terms of grams of solute per 100 grams of water. Now your solvent could be something else. It doesn't have to be water necessarily, but that's typically how we express the solubility of a solute. Now, solubility is temperature sensitive or temperature dependent, and we'll talk about that in a little bit more detail later on. All right, so let's talk about different types of solutions now that we know what they're composed of. So unsaturated solutions contain less than the maximum amount of solute, and you could potentially dissolve more solute. So off to the right, we have a beaker filled with water, and there's some solute in that water, and it's completely dissolved. So it's completely mixed throughout the solvent. So we could dissolve more solute potentially here, and that's what makes it an unsaturated solution. Now, saturated solutions contain the maximum amount of solute that can dissolve. So you won't be able to dissolve any more solute. And in fact, you might have some undissolved solute at the bottom of the container. So I've seen this sometimes with my Starbucks coffees. If they put the syrup into my drink, sometimes when I'm done drinking the coffee, at the very bottom, there's leftover syrup and sugars, and that means that they added too much, right? So they completely saturated the coffee with syrup and sugar, and the syrup and sugar that couldn't dissolve just ended up at the bottom of my cup. You might also see this if you drink tea with sugar. Maybe you added too much sugar and it kind of settles on the bottom because it can't dissolve completely. So that would be a saturated solution. All right, now once you have a solute dissolved in your solvent, and let's say you do have a little bit at the bottom of your cup, so let's say we have our solution here and some of the solute is dissolved, and let's say some is just settled at the bottom of the beaker. Um, what actually happens here is the solute that is in the bottom of the cup is dissolving, and then some of the sugar that's dissolved is going to crystallize or recrystallize. So nothing is sitting stagnant, nothing's sitting still. There's this cycle that goes on in solution where that sugar that's sitting at the bottom of the cup is redissolving. But when it does that, it replaces some of the dissolved sugar. So some of that sugar is going to crystallize. So that's what's shown in this equation at the bottom. We have our solute and solvent initially, and we have the solute dissolving in the solvent to form a saturated solution. So the solute dissolves going in this direction, but you could also have your solute recrystallize and settle to the bottom of your cup. So this is a better picture of what's going on. So let's say initially we have an unsaturated solution, so we're adding sugar or salt or something to our water. But then at a certain point we hit the maximum amount of solute that can dissolve. So that's our saturated solution. So we might see some of the solute settled at the bottom of the beaker because there's just not enough water to dissolve all of that solute. So this is our saturated solution. So again, some of the crystals at the bottom or some of the salt or sugar can dissolve, but when it does that, it's going to replace some of those solute molecules that are dissolved, and those are going to crystallize. All right, so this is just to kind of show you what's happening at a small scale within a solution. So let's talk a little bit about the effect of temperature on solubility. So I said earlier that solubility is temperature dependent, and on the right-hand side here you can see a graph where we have solubility on the y-axis. And again, the units there are grams of solute per 100 grams of water. And then temperature is on the x-axis, and in this case it's in degrees Celsius. So you'll notice that as temperature increases on the x-axis, most of these different molecules have an increase in solubility. So it's easier to dissolve these different compounds at higher temperatures. So glucose is a type of sugar, and you'll notice that its solubility increases with temperature. And that kind of makes sense, right? If we think about iced tea versus hot tea, it's a lot easier to dissolve sugar in hot tea than in cold iced tea. In fact, when you're making sweet iced tea, you want to first add sugar to hot tea and then let it cool because it's much easier to dissolve sugar at hotter temperatures. Now, one interesting thing is sodium chloride or table salt. Notice that its solubility increases only slightly with temperature, so it's not much of an increase there. So salt will dissolve at the same solubility rate, I guess, across most temperatures. But if we look at all of those other compounds, so potassium iodide, potassium nitrate, sodium nitrate, their solubilities increase with temperature. Now, this is not true for gases. The solubility of a gas is going to decrease with increasing temperature. So on this slide, we have a graph of solubility versus temperature again, but this time we're looking at oxygen gas, carbon monoxide gas, and nitrogen gas. And you'll notice that their solubilities are, again, decreasing with increasing temperature. Now, Remember when we were talking about gases, we said that gas particles are really energetic. So they already have a lot of energy. And if we increase the temperature, that's going to add more energy to the gas. So the gas is going to want to escape any liquid that it's in. So for instance, if we have a carbonated beverage, let's say, and there's little, bubbles coming up, if you heat up that carbonated beverage, the gas bubbles here are going to escape even more quickly because they're becoming more energetic with an increase in temperature. So it's a lot easier to carbonate a beverage at lower temperatures, for instance. All right, so that brings us to soluble and insoluble ionic compounds, which we talked about last week, but we'll talk about it again just to make sure we all understand it. So only ionic compounds that contain a soluble cation or anion are soluble in water. And down below we have a table that summarizes some rules that chemists were able to come up with for these different cations and anions. So if you have a group 1 alkali metal ion, like lithium, sodium, or potassium, those will always be soluble. So no matter what they're bonded to, they're going to dissolve in water. And then also included in that category is the ammonium ion, NH4+. That's always soluble. Now, in an insoluble ionic compound, the ionic bonds are way too strong for water to break. So remember previously I told you how water has partial positive and partial negative charges. And it's actually a polar molecule. So let's draw the Lewis structure here for water. So it looks something like that. And oxygen is more electronegative than hydrogen. So oxygen is going to have more ownership over those shared electrons than hydrogen. So that means that oxygen is partially negatively charged and each of the hydrogens is partially positively charged. So water can actually break apart ionic compounds just based on its partial charges, which is really cool. And that works great for us because then we can dissolve sugar or salt or other ionic compounds. However, again, there are some compounds that just cannot be broken apart by water because their bonds are too strong. And so some of those compounds would be, for instance, silver chloride or silver bromide, maybe lead chloride, lead bromide. So if we look down below in our table, we have some soluble negative ions like nitrate and acetate. And then the halogens or halides, when they're ions, they are typically soluble unless they're combined with silver, lead, or mercury, for instance. Sulfate can also be soluble unless it's combined with barium, lead, calcium, strontium, or mercury. Now, I showed you previously a different table, and again, I'm not sure why it's so blurry on the PowerPoint, but I did post it separately on Canvas, so if you want to print out a copy or just keep a copy on your device, you can. But I thought this table was a little bit better at summarizing the different solubility rules. So again, we have generally soluble ions So the group 1A metal ions and ammonium. And then we have nitrate and acetate, and those are all always soluble no matter what. So if you have a compound that contains one of those ions, it will be soluble. But then we get to the halogens, or the halides. And these are generally soluble, again, unless they're paired with silver, mercury, or lead. And then we have the rules for sulfate again. And then down at the bottom, we have some additional ions, and these are generally insoluble. So for instance, hydroxide is generally insoluble, and sulfide is generally insoluble, unless they're paired with something that is always soluble. Or for instance, if sulfur is paired with calcium, strontium, or barium, then it is soluble. Or if hydroxide is paired with calcium, strontium, or barium, it's also sort of soluble. And then carbonate and phosphate, some of our polyatomic ions there, those are generally insoluble unless they're paired with the group 1A metal ions or the ammonium ion. So again, these are just some observations that scientists made, and they kind of came up with a way to organize their observations and turn them into solubility rules. So here are some pictures showing some insoluble compounds. So for instance, cadmium sulfide, or I believe that's cadmium 2 sulfide there. That is an orangish solid precipitate. We have iron 2 sulfide, lead iodide, and then nickel hydroxide. So these are all insoluble compounds. All right, and then this table kind of shows you how to use those solubility rules. So if you want to look at that on your own, you can, but we're going to go over a learning check. So let's predict if the following compounds are soluble or insoluble, and then explain why. All right, so I have on the next slide the solubility rules. So what we'll do is just walk through each of these different compounds. But if you do want to try this on your own first and make some predictions, you can, and then we'll go over it together. Okay, so let's start with A, cadmium sulfide. So we just saw in one of the previous slides that this is insoluble, but if we look at our solubility rules, cadmium isn't listed on this chart, but sulfur is listed on the chart. And this is generally insoluble, so it does not dissolve in water typically. It only dissolves in water if it's bonded to calcium, strontium, or barium. And it's not bonded to either of those, so we're going to say that it's insoluble. So again, that means it does not dissolve in water. Okay, so the reason why, again, is sulfur. Sulfur is generally insoluble. And water is not able to break apart cadmium and sulfide because their bond is so strong. All right, so now let's look at B. We have sodium sulfate. So is this soluble or insoluble? Okay, so let's look at our chart. So we have both sodium and sulfate. All right, so sulfate and sodium are both generally soluble, although sulfate does have some exceptions there. So if sulfate is paired with strontium, barium, lead, silver, or calcium, then it's insoluble, so it won't dissolve. However, in this case, sulfate is bonded to sodium, and sodium is always soluble no matter what it's bonded to. So that means that sodium sulfate as a compound is soluble. So it does dissolve in water. So I guess the reason there would just be that the sodium and sulfate bonds are not that strong, so water can very easily break them apart. All right, so let's look at lead iodide. Now, in a previous slide, we said that this was insoluble, but let's consult our solubility rules. All right, so for this one, we have lead and iodide. I'm going to use a different color here. So I don't see lead listed anywhere, but I do see iodide. And iodide is generally soluble, so typically it does dissolve in water, unless it's paired with silver, mercury, or lead. Okay, so in this case, iodide is bonded to lead, so that means that it's not going to dissolve in water. So this is an insoluble compound. So the lead and iodide bond must be so strong that water cannot break it apart. Okay, and then our last compound is nickel nitrate. Let's see, I think it's nickel 2 nitrate because we have two negative nitrate ions there. And to balance that out, we need a positive 2 on nickel. So this would be nickel 2 nitrate. So just a quick naming there. All right, so let's look at our solubility chart. Okay, and I'll grab a different color here. Let's see, let's choose orange. All right, so I do see nitrate, but I don't see nickel anywhere. However, nitrate is always soluble. There's no exceptions there. So that must mean that our compound, nickel 2 nitrate, is soluble. And that's because nitrate is always soluble no matter what it's bonded to. Okay. So hopefully that helped with kind of figuring out how to use that table a little bit better if you were kind of confused last week. I mentioned last week you'll always have access to that solubility chart, at least in this class. When you go on to general chemistry, it'll kind of be up to the professor whether they allow you to use that table or not on exams. So in the future, you might have to memorize those rules, but for now, I'm going to give those to you so you can consult that table. All right, so let's do one more learning check. We can use solubility rules to predict whether a solid called a precipitate forms when two solutions of ionic compounds are mixed. So what precipitate forms when solutions of lead nitrate and potassium sulfate are mixed? Okay, so this is one of our precipitation reactions potentially. And this is also called a double replacement reaction. So last week we got a lot of practice with this. So let's go through those steps that we talked about. So I'll just rewrite our reactants. And we're going to assume that these are both aqueous. So they're both dissolved in water. And let's see. So we know that lead nitrate can dissolve in water because nitrate is always soluble no matter what. And then we know that potassium sulfate is dissolved or can dissolve in water because potassium is always soluble. All right. So now let's figure out, okay, if these two react, which product would be a solid and which product would be aqueous? All right, so remember, in a double replacement reaction, the metal ions are going to switch places. All right, so let's kind of go through and figure out the charges on each of these ions so that when we make our products, we can balance those charges. So let's start with lead. So lead is bonded to NO3. And we said earlier the charge on nitrate is -1. Now in our compound up above we have two nitrates, so two negatives. So what is the charge on lead? 2+, right? That has to balance out the two negative charges on those two nitrates. Okay, and then what about potassium and sulfate? What is the charge on a potassium ion? So remember, potassium is in group 1A, and that means its charge will always be +1. And then what about sulfate? So sulfate is one of our polyatomic ions, and it always has a 2- charge. Now you could have also figured that out just from the fact that we have two potassium ions in our compound. So that's a total of 2+. So sulfate must be 2- as a result. All right, so now we're kind of doing a switcheroo here. So lead is going to pair up with sulfate, and nitrate is going to pair up with potassium. All right, so that means that our products, let's see, I might not be able to fit them all in there, so we'll just do an arrow here. So our products will be lead paired with sulfate, but let's make sure that their charges are balanced. So we have lead 2+ paired with sulfate 2-. So are those balanced? Yeah, so they balance each other out. So we only need one of each there. And then our other product will be potassium paired with nitrate. So are those charges balanced? Yes, we have a positive and a negative, so we just need one of each there as well. Okay, so now let's figure out which product would be our solid product. Okay, so let's go back to our solubility chart. So we're going to keep lead sulfate and potassium nitrate in mind. And here I'll just erase our notes from earlier. Okay, so we've got lead sulfate and potassium nitrate. So let's see if those are soluble or insoluble. So let's start with lead sulfate. So again, lead isn't really listed in our main ions here, but sulfate is. And sulfate is generally soluble unless it's paired with strontium, barium, lead, silver, or calcium. All right, so that tells us that in this case, lead sulfate is insoluble. All right, so that would be our solid, right? But let's double check with potassium nitrate. All right, so potassium and nitrate. Those are both listed as generally soluble, and there are no exceptions. So that tells us that if potassium and nitrate are forming a compound, their bond is pretty weak. So water can very easily break apart those bonds. So this would be aqueous or dissolved in water. Okay, so let's go back and we will put a S in parentheses next to lead sulfate, and we'll put, oh, I ran out of room. We'll put aqueous in parentheses next to potassium nitrate. Now there's one last thing we should do, which is to balance this reaction. Always remember to balance. So here I'll just, oh, kind of get rid of some of these marks here. Okay. So we're going to make our balancing, my eraser's a little too big here. Let's see, lead, nitrate, potassium sulfate. All right, so we'll make our balancing chart. So reactants versus products. So we have lead 2+, nitrate, potassium, and sulfate. So in the reactants, we have 1 lead ion. In the products, we have 1 lead ion. In the reactants, we have 2 nitrate ions. In the products, we only have 1. In the reactants, we have 2 potassium ions. In the products, we only have 1. And then for sulfate, we have 1 in the reactants and 1 in the products. All right, so let's balance nitrate first. So we need 2 nitrate ions on each side. So let's put a 2 in front of potassium nitrate. All right, so that means we have 2 nitrate ions in the products now. And we also now have 2 potassium ions in the products. Okay, so it looks like everything's balanced. That was super easy. So our coefficients here are 1, 1, 1, and 2. Awesome. Okay, and then, oh, I just had an extra slide here. And here are the solution slides if you need those later. So we're going to stop there today, and in the next video, we're going to talk about reactions with acids and bases. So we're going to talk about what acids are, what bases are, and then what types of reactions occur with acids and bases. So I will see you then.